So our 12 basic functions. Like I said, at this point, I'm just trying to get you to recognize the 12 basic functions, and if you recognize them, you'll know a couple properties about them, a couple properties that we talked about in section 1.2. The very first one is called the identity function because it's y equals x, or f of x equals x. So as long as you recognize that as a straight line is the identity, y equals x, you're in good shape. Domain and range. Well, it points forever in both directions, left and right. It points forever in both directions, up and down. So its domain and range are the same, all real numbers. But we're going to represent that with interval notation. So from negative infinity to positive infinity for both domain and range. It's funny, our book calls the parent quadratic the squaring function. It's a parent quadratic, come on. Y equals x squared, f of x equals x squared. Domain, well, this thing points forever left and right. So its domain is also all real numbers. Oops. But its range, since it has a minimum, this is a bounded below function, just using some of our old vocabulary, its range begins at the y value of 0 with a bracket because it's included and goes up forever. Really easy stuff. So if f of x equals x squared is called the squaring function, then f of x equaling x to the third is called the cubing function, the parent cubic. Well, just like the straight line, the identity function, this thing points up and down forever and left and right forever. Domain and range, all real numbers. So negative infinity to positive infinity. The reciprocal function, f of x equals 1 over x. It points left and right forever, but it does have an infinite discontinuity, a vertical asymptote, right here at the y-axis. So its domain is everything except for x equals 0. So we're going to represent that as a union. So we go from negative infinity to 0, hop over 0, from 0 to infinity. Squeeze it in there. And you know what? Its range is the exact same thing because the y value, every single y value is covered except for y equals 0, the horizontal asymptote. This is one of the ones that does not cross its own horizontal asymptote. So it's identical for the range. Negative infinity up to 0, hop over the y value of 0, and continue on up to positive infinity. So most of these things you've seen before in Algebra 2 honors or even Algebra 1. I don't know if you focus on domain and range all that much. Square root function, that would have been from last year. Its domain, well, because it's a square root, we've already kind of talked about that in 1.2, right? The domain of a square root is all about what's allowed to be underneath that radical. You can't take the square root of negative numbers, but you can take the square root of 0 and any positive number. So the domain begins at 0 and heads on out to positive infinity. So it goes to the right forever. Well, the square root of 0 is 0, so its range also begins at 0. And since we can take the square root of any positive number, we can get y values of any positive number. So heading on up to positive infinity. The exponential function. It's actually the exponential function with the natural base e. Y equals, or f of x equals e to the x. This one does have a horizontal asymptote, but it does not have a vertical asymptote. It just happens to grow really, really fast. So this thing does point forever left and right. Its domain is all real numbers. But since we have a horizontal asymptote, this graph only exists above that. It does not exist below it. So our range is from 0 to positive infinity. Like that. Not including 0. E is a a real number, it's a positive number. There's no way to raise a positive number to any power and ever get the answer 0. Yeah, 2 is an irrational number, so it goes on forever, like pi. It is 2 and change. 2.712, I believe, something like that, or 718, or something like that. 2.72 to 2 decimals, I know that. So we're just trying to identify them. Good so far? Nothing too crazy, nothing too new. I wanted to say too radical, and then, there's a radical right there. But I held back. So 6 on the front, 6 on the back. We just did the parent exponential, so we might as well talk about the parent logarithm, which is its inverse. Now, because they are inverses, the parent exponential has a y value that it can never hit. And when you find inverses, you switch your x and your y's. That means that the parent logarithm has an x value you can never hit. You now have a vertical asymptote. So this thing only exists to the right of x equals 0. So our domain is at 0 to infinity, and our range now is all real numbers. It points up and down forever. Driving home the idea that the logarithm and the exponential are inverses of one another. And I don't know if you remember from algebra, but when you find inverses, you switch the x and the y's and you try to get y by itself, right? Yes, Ms. Rum. Okay, great. Well, maybe you guys noticed that the domain and range of the exponential and the logarithm are exact opposites of one another. The domain and range have switched places. That's because x's and y's have switched places. Now, I don't know what last year looked like for you guys during lockdown, but the hope would have been that somewhere during Algebra 2 Honors, you got to do some trig stuff. That would have been the hope. So we would hope that this isn't the first time that you have seen the parent sine wave. That is f of x equals sine of x. And we will get into a lot of that stuff later in the year. This class is pre-calc and trigonometry. But for now, that is the parent sine wave. It does point left and right forever. So its domain is all real numbers. However, it is a bounded function. It has an upper bound and a lower bound. It goes between -1 and +1 on the y-axis, including -1 and +1. The parent cosine wave is actually just the sine wave that's been shifted over a little bit. And there's a really interesting reason why that's the case, and like I said, we'll talk about it later in the year. But because it is basically the same wave as the sine wave, just shifted over, it is the exact same domain and range. Now, what we're going to be doing in this lesson is focusing on the properties these graphs have. So boundedness, symmetry. Yes?
If like it says cosine x or sine x,
Mm-hmm.
that automatically means the range is -1.
If it just says cosine or sine, then the range is automatically -1 to 1. Now, we could transform it. We could put a number in the front of it, which would be a vertical stretch or a vertical shrink, and we could change that range. So if it says 2 sine of x or 2 cosine of x, then your range has gone from -2 to +2. But we'll focus on graphing our trig stuff towards the end of the trig unit, chapter 6, I think. So you don't have to focus on that too hard right now. In this lesson, we're really just looking at the properties, symmetries, boundedness, domain, range, things like that. Absolute value of x. This one's domain, because it points forever left and right, is all real numbers. There's not a single number that you can't take the absolute value of. But absolute value bars make everything positive. So negatives don't exist. That means you're going to go from 0, including 0, up to positive infinity. And then the last two, this is probably the first time you have ever seen these last two. The last two should be the only new ones. They are the greatest integer function, also known as the floor function, and the logistic function. Okay, let's talk about greatest integer function because it's a wacky one. A few days ago, I can't remember, was Trent? Trent, did you ask me what kind of functions would have discontinuities in them? Or no? Oh, I was close. It came from my back table. What's your name? Brady asked me. So Brady, I'm sorry. Brady, I didn't want to spoil the fun yet, but this, the greatest integer function, is an example of a function that is just chock full of discontinuities. Actually, jump discontinuities. If you asked me what kind of functions could have them, and I said usually it's a piecewise function. However, the greatest integer function and the least integer function, which we don't do in this class, are full of jump discontinuities. What the greatest integer function does is it returns as a y value the integer, the greatest integer that is less than or equal to the number you said. For example, if I said you're working with the greatest integer function and the x value is 2.1, well, the greatest integer that is less than or equal to 2.1 is 2. If you said 2.9, the greatest integer that is less than or equal to 2.9 is 2. So the greatest integer function would give you back the y value of 2 for every number from 2, including 2, all the way up to 3, but not including 3. Because the moment you say 3, jump discontinuity, it gives you back the y value of 3. So it's called the floor function because it takes every number you give it and rounds it down to the last integer. So 3.6 rounds down to 3. Negative 5.8 rounds down to negative 6. Got to be careful because it goes down. Okay, so it just looks like a bunch of steps full of jump discontinuities. Its domain is all real numbers. It hits every single real number. Yeah, the range is tricky. And I want to make sure that I write exactly what I have in my notes. Now, this thing's range. What do you see? What kind of y values is it hitting? Only hits integers. So that means this thing's range does not exist at any decimals anywhere. And the way I wrote that in my notes, because I want to make sure it's exact, range. I just did this. Integers. Because how do you spell this word? Integers? There we go. I don't English very well. Yeah, it doesn't exist at any decimals. Only the integers, positive and negative and 0. It can be represented a couple different ways, and it's important that you recognize all of those ways. So I could just say int of x means integer, greatest integer actually. Or this double braces, double brackets. So I'm going to blow it up because it's a little sketch. It looks like this. And another way that you should be able to recognize it is this one. That's my favorite one. It's not in our book, but that's my favorite one because the bars are underneath the x. So that tells me that's the floor function. It means it slams everything down to the floor. Because the one that we don't do in our class is the ceiling function is this one. Whoops. Habit. It's that. Yeah, that's the least integer function. It's not in our book, so we don't worry about it. But that's why that's my favorite, because it makes it obvious which one I'm looking at. I'll be using one of these two this year. It'll either say int or it'll have the double braces, double brackets, whatever those are called. Okay. And the logistic function. Logistics, you know what? We're all living in a pandemic world right now. The logistic function models things like pandemics. You guys heard all the terminology maybe on the news when they were like, we got to flatten the curve, which meant slow down the growth rate. That's because viruses and things like that grow logistically, not exponentially. It looks exponential for a little while, doesn't it? If you're looking to the left of this line, it looks exponential. Well, not even constant, it can't grow forever. Eventually, you run out of hosts. So what happens is the infection rate would slow down over time, which flattens the curve. And it has a horizontal asymptote up there because, well, there is an upper limit on how many people could be infected. It also models things like ecosystems. The number of individuals that a region could sustain healthily. How many deer could be in an area, things like that. Because eventually you're going to start running out of resources and their reproduction rate will slow down because they're running out of resources, they're starving to death, or there's diseases and things like that. Zombies, well, that's fun. So yeah, so it's used for population growths, viruses, and things like that. It is kind of wacky looking. 1 over, and the denominator of this function is 1 plus e to the negative x. Wow. Its domain, since it points left and right forever, is all real numbers. Now, its range, even though it didn't show that there was a horizontal asymptote on the bottom, it should make sense to you since this models populations and things like that. It's impossible to have a negative population. And we also say that the thing can never actually hit 0, because if it hits 0, then let's just say it's for viruses. If nobody had the virus, how could the virus spread? Technically, it's what you're getting at. If there were no deer to reproduce, how could they reproduce? Something like that. So its range is actually between -1 and +1, not including. Can we vertically stretch that? Yes, not -1. Good catch. Sorry. Sorry. Yeah, negative virus, yeah. Negative individuals are sick today. Sorry about that. There we go. 0 to 1. Good catch. Could we vertically stretch it? Yes, we could. But for now, we're just worried about the parent function. And the rest of this lesson is just about recognizing properties. For example, the logistic function is a bounded function just like sine and cosine. It has an upper bound and a lower bound. And that's it. So we just are going to talk about these properties now. So 9 of the functions have the domain of all real numbers. Which 3 do not? And we legitimately are just going to list the 3 whose domain are not all real numbers. And I can't remember if I did this with words or if I just wrote out the equations. It'd be easier to do it with words, I think. Oh, good, I did it with words. The 3 whose domains are not all real numbers. Square root, because you can't take the square root of negatives. Logarithmic. And the last one, reciprocal, because we cannot divide by 0. This is legitimately what we're doing today. One of our functions has a domain that is all real numbers except 0. Which one? Hint as I just said it. And why isn't 0 in the domain? Well, it's reciprocal. Yeah, so you just say reciprocal, how do you spell this word? Reciprocal because, I'm not going to write because, just B/C, because you can't divide by 0. Can't remember if I've been over this with you guys or not, but I always cross my Z's. That way you won't think they're 2's, and you won't think my 2's are my Z's, because I always cross my Z's. Part C, which 2 functions have no negative numbers in their domains? Well, we know it's one of the 3 that we said in part A, right? The 2 of the 3 that we said in part A. So the ones that you can't have negative numbers for, well, you can't take the square root of negative numbers. Reciprocals of negatives exist, so it must be logarithmic. Whoa. Combine my H and my M. There we go. So we have square root and we have logarithmic. Which one is defined at 0? You could take the square root of 0. So square root is defined at 0. Cheating and just writing it underneath it. So yeah, today's lesson is easy peasy. You're just looking at the pictures, getting familiar with your 12 basic functions. Talking about continuity. Only 2 of the 12 functions have points of discontinuity. It wants to know, are these points in the domain? So, The easy one that has points of discontinuity, the integer function, greatest integer function. And the other one with points of discontinuity in its function. And the reciprocal. Just so we're clear, I am aware that the logarithmic function has a vertical asymptote, but that is not considered a point of discontinuity because our graph only approaches it on one side. If it approached it on both sides, then we would have to call that also a graph with a point of discontinuity. But we only exist in the positive realm. So the other one is the reciprocal function. I can't spell. So in the greatest integer function, our domain was all real numbers, wasn't it? So even though we had points of discontinuity, jump discontinuities at every integer value, those integers were still in my domain. They were a closed dot somewhere, right? That's the definition of a jump discontinuity. It's an open dot and a closed dot. Tell him to go get a drink of water or something. He's not going to make it. Anyway, so yeah, the greatest integer function, are the discontinuities in the domain? Of course they are. So yeah, we could say they are in the domain for this one. But the reciprocal function at its infinite discontinuity, that happens at x equals 0. Is x equals 0 in our domain? No. You were never allowed to divide by 0. 0 is not part of the domain. So x equals 0, not in domain. And that's actually a pretty important concept because your textbook defined a continuous function as a function that was smooth and it had no breaks or jumps in it, right? So then the question is the reciprocal function a continuous function? Just out of curiosity, raise a hand to people who, so we're going to take a vote. Continuous function, so is the reciprocal function continuous? Hands up. So 1. So is the reciprocal function not continuous? Basically everybody else. Max, you're the right one. The reciprocal function is considered continuous. But why? Because the point x equals 0 is not part of its domain. So you can't ask yourself, is it breaking the rules of continuous at x equals 0? It was never one of the points you were allowed to talk about anyway. And that's why I don't like this book's definition of continuous, because it makes you think that the reciprocal function is a discontinuous function, when in reality, by definition, it is still continuous. And that's kind of a weird thing to think about right now. Luckily, I get to teach you calculus this year, and when I teach you some calculus in quarter 4, I can give you a concrete definition of continuous, and it will make sense why the reciprocal function is a continuous function. Whereas the integer function, the greatest integer function, well, it's full of jump discontinuities. And since those values are in your domain, it is by definition a discontinuous function. Yes, sir?
How is it continuous if like it doesn't overlap at all?
So he wants to know, how can we call it continuous since you can't be at x equals 0, is what he's wondering. Well, technically, and that's why I don't like, remember when I said, okay, for now, our definition of continuous is a smooth curve with no breaks in it? And I said for now, because that's a really, let's just be real, that's a crap definition of continuous. What it should have said is the function exists at every point in its domain and is smooth on all of those points. That's what it should have said. Because it doesn't exist at x equals 0. X equals 0 is not in its domain, so it doesn't break the rules, because every value of x that is in its domain, the function is smooth with no breaks in it. That's why. So I hate your book's definition, and that's just the way they say it to pre-calc students for some reason. It's almost as if they think you're never going to go learn calculus. How hard is it to include what I just said and say on its domain? But the book doesn't. But that's why. Because the reciprocal function x equals 0 is not in its domain. You can't ask yourself, is it breaking the rules at that point? It simply doesn't exist there. Whereas the greatest integer function exists at every single number, and I could say, but we have breaks at every integer, even though they're in my domain. Only 3 of the 12 functions are bounded either above, or bounded, meaning above and below. Which 3? Shout one out, somebody. Logistic is 1. That one's bounded above and below. Well, bounded means gets stuck between two values. Sine is 1, and cosine is the other. There it is. Sine, cosine, and logistic. They are bounded functions. Now, it doesn't ask. The parent squaring function, the quadratic, it's bounded below, but it's not a bounded function. And the square root function is also bounded below. I'm trying to think of anything else. Exponential is bounded below. Absolute value is bounded below. Yeah, I knew there was one more, but I couldn't remember which one. Looking for symmetry. 3 of the 12 basic functions are even, and just to remind you of what that means, because we did that yesterday, an even function means that the y-axis acts as an axis of symmetry. That if you could fold it in half perfectly over the y-axis. 3 of them are even. Absolute value is 1. Hope you guys don't mind, but I'm going to see this. Too lazy to write it all. Absolute value is 1. Cosine, good catch. Cosine is an even function. And then the last one, squaring, x squared. There it is. Those are the 3 evens. And then there's some odd functions. I don't remember if that's what's going to happen next or not. I don't want to spoil the fun. Odd ones, sine, cubic. Trying to think of anything else. Odd and cubic or a sine and cubic are both odd. The reciprocal's odd, good. And I believe greatest integer is odd. I believe. Yeah. Okay. It may or may not be. I can't see it very well in my head right now.
I don't think it is.
It might not be. The least. I'm sorry. Oh yeah, and the identity function's odd too. Yep. So we're going to graph this thing, this very simple quadratic, and then we're just going to ask some questions about it. Very simple questions. Well, I'm hoping that everybody can see instantly where its vertex is. The vertex is whatever makes the inside equal 0, comma, the number that's added or subtracted to the far right. That puts our vertex at 2, 0. Just in case, because we haven't done it, but vertex form of a quadratic, where vertex is at h, k, whatever makes the inside equal 0, comma, the number that's been added or subtracted to the far right. That puts us at 2, 0. I guess what we could do now is we could just go to the left or right by 1, just plug it in and see what we get. Let's plug in x equals 3. At x equals 3, we have 3 minus 2, 1, and square it, 1. And since parabolas are symmetric, we'll have a dot here as well, and then we'll just do something like that. Ta-da. I'm not going to lie, it's a pretty good parabola. If I do say so myself. Not a single chuckle. That's okay. I'll get you guys one of these days. Part A is about increasing and decreasing.
I'm sorry,
If you are slap tired, then it should be even funnier. Alrighty, talking about increasing, decreasing. Where does this thing increase? Somebody raise a hand for me, tell me. From positive 2 to infinity. Good. So we are increasing after our axis of symmetry. And remember, at the boundary, please don't use a bracket. I don't care what your authors of your textbook say, they're wrong. So increase from 2 to infinity, because that's where your roller coaster would be going up if you were riding this thing, right? That means decreasing is going to happen on the other side. We read our graphs from left to right, so from negative infinity to the far left, all the way up to the value x equals 2. So you're looking at this thing, and you ask yourself, does it have symmetry? Is it even, odd, or neither? Everybody at once, shout one out. Everybody said even. That was awesome. Everybody's wrong. It's neither. Remember, now here's what happened to you guys. Here's what happened to you guys. I love that result. I love that. That was awesome. You guys can't see, but I'm smiling like a huge big old nerd over here. Here's what happened. The parent quadratic is even because it's symmetric over the y-axis. But this thing does not have even or odd symmetry. Is it a symmetric graph over its own axis of symmetry? Sure it is, but that doesn't make it even. It's only even if it's symmetric over the y-axis, and this one is not symmetric over the y-axis. So this one actually is neither. It has no symmetry according to the y-axis or the origin. That was fun. That was really cool, actually. I like that a lot. That was fun. Thank you. Does this function have any extrema, which is what we talked about yesterday, maximums or minimums? Yeah. Then the answer is yeah. Yeah, it has a minimum. Remember, extrema, maximums or minimums, will happen every time you change from increasing to decreasing or decreasing to increasing. Basically, the top of a bump or at the bottom of a bump. That's where you're going to find extrema. So yeah, every quadratic has either a minimum or a maximum. And then how does this one relate to its parent y equals x squared function? How's it different? Yeah, literally we used a transformation and we shifted it right 2 units. So the parent function shifted right 2 units, lands on that one. I hope we're finding this lesson easy.
I have a quick question.
Yes, McKinley, what's up?
For increasing, if you wrote infinity to 0, would that be the exact same?
Unfortunately not. So because we read our graphs from left to right, we have, whenever you're writing your interval notation, it has to be from small to big, always.
All right.
So we would have to say from 2 to infinity.
All right. So if you said from 2 to, so if for increasing you said 2 to negative to infinity, that would be the exact same as 2 dash infinity. Or what you have written right now, I mean.
Well, we're increasing to the right of the axis of symmetry. So you'd have to say from x equals 2 to positive infinity.
Okay.
But for decreasing, because negative infinity is the, how do I say this term? The most negative thing that we can imagine. It is technically the smallest thing we can imagine, so we would have to write the negative infinity first. So if you're going to mention infinities, negative infinity always comes first, positive infinity always comes last. It's just how it always works. Piecewise function.
Positive infinity comes first or second?
Positive infinity always comes second. Negative infinity always comes first. Because negative infinity is the most negative thing we can imagine, and positive infinity is the most positive thing. What a strange thing to say. Is the biggest number, the biggest thought we can imagine.
So if you were writing a negative infinity, would you write the x next to it or the y?
Oh, we don't ever worry about the x's. You don't write the x's. What you would do is typically you would have a capital D for domain or a capital R for range. So if the question asks about domain, you don't even have to say the letter x because it's
not
known.
For the domain. I mean the increasing. Would you write the x or the y? Because you wrote
okay, I got what you're saying now. When you're talking about increasing and decreasing, and I don't know if I made that clear enough. When we're talking about increasing and decreasing, we're only talking about on what x's is this happening. So when you're talking about increasing and decreasing, you don't actually worry about what the y's are doing. You just say, if I was standing on this x, was my roller coaster falling or was it rising? So yeah, so that one's always, you're always listing x values. On which x values is the graph doing this? That's a good question. So it says, which of the 12 basic functions does this piecewise function model? So it says the function looks like y equals x when x is greater than or equal to 0. But the function looks like negative x when x is smaller than 0. In case you can't see it in your head, let's just sketch it real quick. So if we're talking about x's that are greater than or equal to 0, it looks like y equals x this way. And it has a equal to bar, so we have a nice closed dot there. But for negative x's, it looks like y equals negative x. Well, that's this, with an open dot. So that one has an open dot with a closed dot inside it. That piecewise function models the absolute value function. That's how you would break it up into two other functions. Algebra 1 would have been the only time that you graphed piecewise probably. And even then it was probably not done very much, right? So I've noticed in the past that the students struggle a little bit graphing piecewise functions. If you are struggling with graphing piecewise functions when you go to do the homeworks or when you're doing the practice tests and things like that, please let me know so we can practice a little bit more. So I've given you a piecewise graph this time, and we've been asked to use the 12 basic functions to make a piecewise definition. So the thing that you just had up there, the f of x equals with the big brace, that is your piecewise definition, and we have been asked to do that for this. So you look at your picture, and you just decide what two things is it made out of. I like to read my graphs from left to right, so I kind of take issue with the first one that they gave us because they gave us the right side before the left side. I'm sure that there's not a that's the correct way or that's the incorrect way. I just like doing the left side first and then the right side because, you know, x domains, all that crap goes from left to right. On the left side of this thing, what kind of graph are we looking at? Yeah, to the left of that blue line right there, there's a lot of blue lines. But to the left of that y-axis, that thing's quadratic. What in the world just happened to me? One too many times. So the parent quadratic is x squared. So this graph looks like x squared as long as x is less than or equal to 0. And what does it look like to the right? You're thinking of the logarithmic.
X squared if x is greater than 0?
Well, if it was x squared, it would be the other side of the parabola, like that. So it does kind of look like logarithmic. However, we can see that it's hitting the origin, so it can't be logarithmic. But it would be the square root function. To the right side, we have the square root of x as long as x is greater than 0. Now, I'm not going to say greater than or equal to because I included the 0 on the x squared. And that was a choice I made. I could have either included that 0 on x squared or on square root of x. You just can't include it on both. That doesn't.
Why can't you include it on both?
Because if you include it on both, it is technically not a function because you have an x that can plug into two different equations. And there's a possibility that it could be giving you two different y's. For example, let's just pretend, and you guys don't need to draw this clearly because you don't have the ability to do what I'm doing. I erase a function because it could have been like this. And the only thing that would have changed is I could have just stuck a +1 like that. Now, if you include 0 on both of them, and I say, hey, what is y when x is 0? You go, oh, well, it's 0 and 1 at the same time. Now it's not a function. So you have to make sure that that equal to bar only happens on one of the two domains. And it doesn't matter which one you choose. You pick one, either the top one or the bottom one. It doesn't matter. What do we think? Not too bad, right? It's not too scary. All right. And then on to our last page. 21. 21, so you're going to want to leave now. That clock is slow. It's 16 after right now. So this is y equals ln of x. It's simply asking, does it have a horizontal asymptote? What do we say? Yes or no?
It does.
Someone, I think, in the back said the magic word. What kind of asymptote does it have? Has a vertical asymptote. This thing, the vertical asymptote, is right there. But even though it looks like it's flattening out to the right, it's technically not. It will grow forever. So this one does not have, so does it have a horizontal asymptote? No. Vertical. Now, the parent exponential is its inverse. The parent exponential does have a horizontal asymptote. That's why this one has a vertical asymptote. Because they're inverses. X's and Y's have switched. That means domain and range have switched. So does it look like it's flattening out? Yes, it does. But it's technically not. See, there's a difference between logarithmic and logistic. Logistic does have horizontal asymptotes. Logarithmic does not. So for this one, it just says give a complete analysis. That means you just list out all the stuff you can about its symmetry, decreasing, increasing, maximums, minimums, domain, range, continuity, and boundedness. That's a complete analysis. First of all, symmetry. Does it have symmetry? What kind? Even or odd? It's an even function, so we'll say it's even. Let's list its domain. That's just its x values. All real numbers, negative infinity to positive infinity. Its range. All positive numbers and 0. So we're going to include 0 to infinity. Increasing. Which side is it increasing, left or right? Right side. Yeah. So we increase from 0 to positive infinity. Those are the x values. We're only talking about the x values when we say that. Well, if it's increasing on the right side, then we know it's decreasing on the left side. So it's decreasing from x equals negative infinity, which is impossible because that's not a number, to x equals 0, not including 0. Because 0 was a change between increasing and decreasing, we know we have an extrema there. It's either a maximum or a minimum, and this one is a minimum. Its minimum value is 0. So it is a minimum at 0, 0. When you say what is the minimum, what is the maximum, you're talking about the y value. But I've told you where it happened. Oh, I have a minimum at the coordinates of 0, 0. What else? Bounded below. Awesome. Was that the last thing on here? And one more. It's going to be a really obvious one. It's continuous. Meaning it has no breaks on any of the numbers on its domain. Will I ever ask you to?
Yeah.
I think in the homework you have to do one maybe, but I'm not going to put that on a test if that's what you're asking. Let's just say you forgot to list one. Yeah, that's why I don't put it on a test. What I would do instead is say I would just list out all the stuff. And I would just ask that you filled it all out. Because it would be kind of tricky for me to see you do that, right? Like, you forgot to say it was continuous because it was so obvious. You know, that wouldn't be fair. So that's why I would never do that to you.